Yes. All right. Welcome back. And it's the end. It's the last day, and we've got a few things to do today. I want to go and do a long step-by-step review of the course topics so that you're all clear on what the focus on the exam is. And then we have course evaluation, and then I'll finish with a discussion about the actual exam itself coming up in 2 weeks. So let's get started and see. Hopefully this won't take too long. Let's see what happens here. So let's go through all the subjects that we've covered in this semester. And as I assembled this, some days went fast, some days went slow, some days were fuller than others. But I think we did a pretty good job of covering what the advertising says. I think we did pretty good about living up to what's written on the outside of the box. But now that I've done this once, I think there's actually a little bit of lift in the plan, and next year I think I'll be able to actually set one more chapter into the class. But otherwise, I think we did pretty good. Otherwise, we covered the material that I wanted to cover and that we promised we would cover, and I covered it at a rate and a level of difficulty that I think was appropriate for this class. So let's remember what we did here. We started the semester before break, and we just started. Some of this maybe was a little bit of review from your previous statistics class, but it's really important. So it was worth covering it again, and it was worth making sure that you really understood this because it's so critical to what comes later in the course. So we went back over, we started with statistical process control. We talked about setting confidence intervals, and we talked about the normal distribution, and we talked about the T statistic. And we said, look, these are foundation. This is like, this is like the Grunlow. I mean, this is foundation for everything we're doing, right? So we talked about statistical process control and setting limits on the mean of a sample. And we talked about different ways that this could be done. That is, when we know certain information about the data, and then when we do not know certain information about the data. So this question about is the variance known or not known, and what defines known, right? Well, I'm sorry, there's no that's what you decide. It's a matter of confidence in your data and confidence in your knowledge, and whether you know the variance or don't know the variance is entirely a political decision. It is entirely we decide that we know it or we don't, and that's the truth. And then we talked about hypothesis tests, and I really pushed you to think about this graphically. Really think about this graphically so that you clearly know what it is this is about. And then we talked about, again, known variance and unknown variance. And we talked about, I showed it graphically, and then we said, okay, when you're in a hurry, how do you do this just with numerics, with numbers, with calculations? And then we went through the functions in Excel. We learned how to do this in Excel. And then we learned how to do this for comparisons of variance. We looked at quadrature, we looked at squares. How do we make judgments about statistics based on multiples? And the answer is we use a chi-square distribution. A chi-square distribution is for things where we are talking about multiples of things. So we did the chi-square. And again, we were still in Excel at this point, still doing this in Excel. And then we closed out our talk about goodness of fit with goodness of fit for a distribution. And we talked about doing it here with this chi-square test. And we did this manually and learned how to check a distribution against a known correct sample and make a decision about whether the data we had really fit that distribution or not. And so, for example, every time you run a normal probability plot in R for a linear regression, you are basically doing a goodness of fit test like this. It's graphical, it's not doing this numerically, but you can generate the numerical results just as easily with a couple extra commands that essentially duplicate this. But what's going on in this goodness of fit test is exactly the same as what you see when you do the normal probability plot and you see where is the data sitting with respect to where you think it should be. And then we finished out with a couple more examples of comparison of variances. And then we talked about this question of errors, type 1 and type 2 errors. And we said, hey, you know, these measurements are not magical, correct, always perfect numbers. They are ultimately a guess. They are an educated guess. They are a prediction of what we think is correct. We could be wrong. And what is the probability that we're wrong? And so this type 1 and type 2 error is about what is the probability that we're wrong? What is the probability that this prediction we're making is incorrect? And all of our regression contains type 1 and type 2 errors. All of our regression is a guess. And it could be that the models we make in our regression are entirely wrong and that we just got a random sample of data that was not correct or unusual in some way. And then we finally started with linear regression. And at the very beginning, we started with pure Ren linear regression and with this functional form. And there were a number of key assumptions, key förutsättningar that really are necessary to say that the models we create are correct. But then we learned that in reality, it's very unusual to have a data set that all of these things are completely true. So we have to compromise. But we look at these problems and we say, how badly does our data deviate from these förutsättningar? And we have to make a judgment. We have to make a decision. Will we accept the difference between our model and theoretical reality or not? And there's a scale, right? It's really, really bad, better, okay, really good, really, really good, right? And we just have to kind of make a decision about what we're going to do. But these are the key things to look for. And these are shown in many of the plots that we generate, many of the statistics we generate when we're looking at our regression. And then we paid a lot of attention to errors. This is a really important thing. We look at residual plots and we look at the errors because this is a major information source in our model. And then we learned how to run these models in R and how to generate these plots in R. We did that. And then we expanded. And here's our plot. We learned how to read these plots. And then we addressed this question of how to deal with data that's not really real valued, data that's really descriptive, data that says you're a man or a woman. Well, it's not a number, it's just descriptive. How do we code that data into our models? And we learned how to code it with binary variables. And we did that. And here's an example. We did this. We transformed this class of data we had, which is not really numerical, it's just a label. And how do we transfer that into something that the mathematical program can really deal with better? And then we learned how to do larger linear regressions with multiple variables. And then that raised the question, if we have lots of variables, do we always use all of them? Or should we not use all of them? And how do we choose which ones we use? We learned how to interpret these data tables, these coefficients, and how to do some calculations based on them. How to calculate the goodness of fit. So what does R squared really mean? And we learned that R squared is important, but we also learned that coefficient significance is important. And we learned that these two things don't always go together. The R squared and the coefficient significance can be independent of each other somewhat. And so then we learned how to calculate coefficient ranges, probability ranges. And there's commands in R to generate these tables as well. And that gives us some sense of how tight our model is. And then again, how to judge which variables to keep in the model and which ones not. And, you know, is it really always a good thing to have more variables in the model? And the answer is not often. No, it's not. We learned about this thing called AIC, which is relatively new and which is also relatively popular today in judging model quality, which models are better than others. And we learned that R uses this a lot. So we learned how to run some code to generate stepwise regression to fit a model in R. And we learned that R has a lot of functions that depend on AIC as the judgment, as the measurement quality for which models are better than others and how to fit extra variables. And then we learned about best subsets. And we learned that there are limits to this because best subsets could cause your computer to consume an enormous amount of processing time, so that it's actually, for larger models, for larger data sets, it's actually completely impossible to run all possible best subsets. And so you have to, so the example we've been using in our code is an example that intelligently just picks us a group of examples. So the code that we've been using in R does not actually run all best subsets. The code we've been using uses some kind of decision-making tree and only looks in areas where it thinks it has a really good chance of finding good models. So it's not the same as stepwise, because stepwise is literally step, 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 one at a time. I'm going to step through the variables, whereas best subsets is like, well, let's look over here. Oh no, let's look over here. Oh no, let's look over here. And it kind of says, well, looks good over here. Let's grab this one. And so it's a little different way of thinking of the problem. And we learned that there's a couple of different codes in R to do this for us. There's leaps, which we use because it creates a really pretty picture, but it doesn't really have as much power and capability as the GL multi. I received a lot of comments from people saying they couldn't get this to install on their computer, but no one ever contacted me to go any further or actually solve this. So either you solved it or you just decided you weren't going to do it. So we're kind of running out of time now, but I understand some people had a hard time getting this to install, but I didn't, no one pursued it any further with me. So that's kind of, that ship has sailed. But this is a very popular package, and there are online comments about, okay, how do you solve installation with this thing? But it's a very popular package. And then we talked, actually probably a little before these lectures, we talked about transformations. We talked about looking at the residual plot and then making some judgments about the data and saying, hey, maybe I should try transforming my data to make it fit better. And then we actually looked at a paper, published paper on railway delays, and that author transformed the data with a log. And that we noticed made a big difference, made a big difference in the fit of the regression. It was a big change when we transformed the data. So we learned that that's something to seriously consider. And it's experimental. You have to try it and see what happens. And then here's the Y transformations. And you can see the cone pattern there. So the transformation also can be very helpful in managing this cone and getting rid of this cone in the data. And then we went to stochastic regression. And in stochastic regression, we were trying to fit a probability distribution, a random probability distribution to the output variable, to the Y variable. And so this is a totally different kind of exercise than the linear regression, the ordinary least squares linear regression. And we had to learn that we need to do this with a likelihood fit. And this is something you really can't do by hand. It's not going to happen. And so it requires a lot of computer power, and it definitely requires specialized code in your computer. And it requires R or SAS or something like that. But we learned how to do this, how to fit these functions with R. And there's a function in R called multinom, and we use that to fit these distributions. And then we learned about the Poisson distribution. And we learned that this is very similar to multinom. And I also learned in grading your homework that some people did not understand the difference between these two. And you need to be a little bit eyes open and think, okay, do I want multinom or do I want Poisson? Because they are different, and you kind of need to realize what it is your data is doing and be clear about which one you need to pick. So that's important. But we learned Poisson distribution, and this is particularly important for processes that have some kind of random arrival pattern. Traffic on a highway, customers arriving to a store, failures of machinery, breakdowns of machinery. These are all Poisson distributions very often. And we learned how to code this and do this in R using the GLM function. And then we have for both of these, and this again is something people missed. So for both multinomial and for Poisson, we learned that there are tests we can use to judge the quality of our models. And these tests are valid for both of those models. The log likelihood test, and we learned about the McFadden statistic. And so we learned the code, and the code for these is not very hard, but one little keystroke mistake and you get the wrong answer. So you have to be really careful about your work. And the number of degrees of freedom is important, because one keystroke mistake on the degrees of freedom and you get the wrong answer. So watching your degrees of freedom is really important in doing this, because it can get really deceiving. It looks really easy, and then you realize, oops, I did the wrong thing. And the McFadden statistics, same thing here. These are really easy commands to run, but you just got to slow down and make sure you're doing it right. You know, it's like cycling, you know, brutto secondo me. You know, stop and look for a minute, get your nose out of your phone. But anyway, so these two statistics are really important. We can use them to judge the quality of a model alone, and we can use them to compare two different models, particularly the log likelihood, not the McFadden so much. McFadden is pretty much just for a null fit, but the log likelihood can be used to compare two different models against each other, which would be really important in something like some kind of stepwise regression or something. And then we talked about outliers, and we really closed out the last week or two of our semester with this looking at model diagnostics, looking at outliers and things. And what is an outlier? How do we define an outlier? And what is Cook's distance? And how can we use Cook's distance to help us identify outliers? And how can we generate these plots in R to give us this question, to give us this answer? So we did that. And then that brings us to today's paper discussion. And I'm pleased at the time I'm using good time so we can do this and then have a break and come back. Or maybe even, we'll do this and then have a break. So this paper, I asked you to read this, and I hope you did. Otherwise, it'll go pretty quick here because there's not much point in my just giving a speech about the paper if you haven't actually read it. So I guess I should start here before I just jump into a discussion about this paper. Does anybody have any comments about this paper? What parts of it did you find easy to understand, and what parts were you like, I don't know what the heck these guys are talking about? What did you think about this paper about BART?
Maybe a question should be how many actually read it.
Yeah, well, if you didn't read it, then we're going to just skip this, but it's too bad because this is practice for the exam. Because the exam is going to have a paper on it like this. Did no one read the paper? Okay, I'm going to take that as no one read the paper. The key thing, I'm going to summarize what's important about this paper, but just warn you that, one of the things I want to do in this course, which I think is valuable, is to go beyond just memorizing the textbook and answering some questions. And that means seeing how we apply this in the real world and for transport, because we're a transport course, remember? And so it's important that we look at some real applications in transport and see how this goes. But this paper is all about a fairly common question like, hey, I built this really expensive transport system. Did I get anything for it? I mean, is it worth the effort? And so this paper is really evaluating growth. It's evaluating construction growth as a result of the BART transit system, the BART subway in San Francisco, which was a big, big deal. BART was a big deal in the 1970s. It was a rocket ship. For you guys in Europe, it's like, yeah, well, big deal. They built a subway. What a bunch of morons. But for America, it was like rocket science. It was just rocket science. And I lived here as a little boy in the San Francisco area. And I remember my parents because they knew I liked trains as a little boy. I remember my parents took me on a ride on BART when it opened, like in the first week. And they took on a Saturday or something, they took me on a ride on BART. And it was a big deal because we were just the typical Americans living in a suburb, in an automobile suburb. So we had no public transport around us ever. I mean, public transport, what's that? I never rode a bus growing up as a little boy. We drove everywhere. And so this was a big deal. So we had to drive, it was like a family tour. We got in the car and we drove to, I believe we drove to Fremont Station, which is on the map in this paper. We drove to Fremont Station, parked in the big, big parking lot, huge park. It was like going to the mall. It was like a giant parking lot, park at Fremont Station and get on the train. And it was just rocket science. This idea is just like, people had never seen this before outside of New York City. They'd never seen this before. It's like, wow, okay, there's trains, and and it was really revolutionary because of the ticket as well, because BART was the first system in the US to implement a zone fare. And it was a big deal. They had a little paper magnetic ticket, which I think they still use, a little paper magnetic ticket with a magnetic stripe on it. And you put money on the ticket. And today we're like, we do this all the time. But in 1972, this was like, wow. And so you put money on this ticket, and then you have the gates at the station, and you feed the ticket into the gate, right? And the gate would stamp the ticket and encode the magnetic stripe with what station you got on. And then you would go ride the BART. And then when you left at the other end, you put your ticket in, and it would stamp the ticket and read the magnetic code and deduct the money from the ticket. Well, sounds great, right? Sounds perfect. It was a disaster. It was a disaster because it was so foreign to everybody. Nobody had a clue how this would work. And people were used to the idea of paying for one ticket at a time. So what would happen is they would go to the ticket machine and they would look at the map, and the map would say something, and the map was impossible to understand. And the map would say something like, you're at this station, and there'd be a number written next to it. And that number wasn't the fare for you to go somewhere else. That number was the fare for you to go to where you already were. And so people would buy tickets with the wrong amount of money on it, you know, and they'd have trouble getting their dollar bills to go into the automatic machines because there was no people selling tickets. It was all automated. It was all automated machines. So anyway, so my parents didn't do it right. They didn't put the right amount of money in the machine, and then we went to the turn gate to get in. The machine to take the ticket, and they didn't realize they had to walk forward before the gate closed. So they put the ticket in, and then the gate closed before they walked through, and then they had to like try to come through. Then they like picked me and my brother up and carried me through the gate because it was just finally security guard had to come out and let us through and everything. But lots of people had that problem. And in the first few months of the operation, it was just a huge learning experience. Nobody had a clue how to really make this work properly. And it was just crazy. But anyway, it was a big investment, huge project, very modern, very modern equipment, very high tech. And there was a lot of questions of, is this really doing anything? I mean, we just spent hundreds of millions of dollars building this elevated subway through San Francisco. Does it matter? Is it actually developing the property? Is it bringing any economic gain? And so these guys were looking at this and saying, what is the economic gain of doing this? And at the very end of this paper, they use regression. At the very end of this paper, they use regression for some data sets to analyze whether or not this is really going anywhere. And just to quickly summarize, they want to see whether there's residential or business growth in the real estate. And it's pretty obvious from some of the collected data that the BART system was a huge impact on high density office building growth. So it had a huge impact on downtown San Francisco, but it did not have a big impact on residential growth. That is, what BART did is it created a giant transport system to move people from the suburbs into jobs at the office in the city center, but it didn't do anything else for most of the towns around it. It didn't stimulate any residential growth. It didn't stimulate more dense residential development. It didn't change their living patterns outside of San Francisco. A large number of people were just driving their cars to park and ride lots and then taking the BART. All it was doing was saving them the automobile toll across the Bay Bridge and the congestion on the Bay Bridge. And so it didn't have a huge impact in terms of changing people's life standard and changing the way they live their life, which was very disappointing for a lot of people about the system. But here's that linear regression model, and we look at this here's the table of the results. And the reason this analysis is important is because very often you're going to read a paper that uses linear regression. And of course, you don't have the data. You just have the results that they published in the paper. So you got to figure out how to read these results and judge whether this model is any good or not, and whether or not the results that were published actually mean something to you. So, here are their results here in the paper. And it's pretty straightforward, and it looks like the coefficients are all significant, except maybe the dwelling units. And we have an R squared of 0.6 is not bad. The model is statistically significant with a p-value of almost null. And so in the exam, I could easily ask you, okay, what's the fitted equation for this model? Give me some results off of this. What do you think about the quality of this model? And And so here we look at this. So here is the fitted equation based on this table of data. And you see these effects down here. Now, something we did not spend a lot of time on in this class, but which maybe I'll have time to in the next year, is we didn't spend a lot of time discussing how to interpret these coefficients. We didn't spend a lot of time saying, okay, what does that coefficient really mean for me? How do I judge that? You know, we didn't do that. And I was just running for time, but I think next year I'll have time to do it. I think next year I'll be able to put in a couple of hours and say, hey, let's talk about the how to read these coefficients and what they really mean. You know, one of the things to do here is they have these two models. They have table 5 and 6. They both use the same data set. They're both the same 25 stations. The only difference actually really is they have a few different X variables, and they have the output Y is different. One is concerned about residential property, and the other one is concerned about non-residential property. So an interesting comparison here would be, are any of these X factors more important to residential or non-residential property? And so we could look at that here, and you look at the data sets, and there are a couple they have in common. They both look at park and ride spaces. They both look at the distance to the motorway. And then you're kind of like, well, then they lose a comparison. And there's like, well, maybe you could compare employees and how many residential housing units there are. But you can look at the data and you can see that park and ride is clearly more important to non-residential development than residential. And you know why? I don't know. Paper doesn't say. My hypothesis is that people who are driving to a station to park their car are also more likely to do shopping while they're at the station. They are more likely to get off the train, go shopping, fill their car with stuff, and then drive home. And so that my argument would be that the areas around stations with large park and ride lots are areas that are very attractive to build grocery stores and office space and small boutiques and shopping. And that would be my argument. And that would be my, you know, it's been a long time since I've actually looked at the satellite photos of these stations or thought about it. And I don't have access to satellite photos from 30 years ago. So, but my memory seems to fit with that. My memory of San Francisco and the Bay Area would be that Fremont Station, Concord Station, stations with large park and ride lots were surrounded by strip malls, restaurants, grocery stores, hardware stores, sports goods stores, things like this. And people were shopping on their way to or from work, probably from work more than to work, and then picking up stuff and putting it in their car on the way home. And you see motorways are a little less valuable to non-residential. And that kind of stands to reason too, because if there's a motorway really close to the station, there's a real attraction to just jump in your car and go and get on the motorway and get away. And so the further away the motorway is, the more likely you're in your car and you're driving around and you stop at one of the shopping places nearby the station. That's kind of my estimate on things. But then we can run some statistics here. We learned in our code to generate confidence intervals and coefficients automatically by just typing in some keystrokes. Here you have this data table from the paper. And so how do you generate? You've got to do this by the hard way. You've got to generate the confidence interval manually, but they give you enough data to do it. They give you the standard error, and we could do that. And if you look at the, for example, for parking spaces, and you compare the confidence intervals on the ranges for the two different tables for residential and for non-residential, you know, at first you say, okay, there's a difference. I said earlier, okay, there's a 2 times difference between non-residential and residential, but yeah, there's a difference, but the confidence intervals overlap with each other a lot, actually. And statistically, you could also argue that they're not different. you could argue it's just a random sampling error. And with only 25 stations, only 25 data points in the data, could be a problem. Could be that this data does not in fact show a difference, and that there's no difference in park and ride spaces between non-residential and residential growth. Could be. The way to solve this would be to have more data, more stations, but we don't have more stations. The BART system only has, in 1997, only has so many train stations. It's not like you can just manufacture more train stations and get more data. So you're stuck. You only have this many degrees of freedom because that's all the data is going to give you. And complaining about that won't get you anywhere. It won't make any better results. So the author's conclusions are pretty much matching with what I just said. And so this was a little disappointing to a lot of people, a lot of planners in California in the early 1970s and 1980s, that they'd spent so much money on this transport system. And it was important, you know, it was important to the economic development of San Francisco, but it didn't really have the kind of transformative effect on people's lives that many developers had hoped, that many planners had hoped. It didn't really change lifestyles in the Bay Area. And I can say from personal experience that outside of the center city of San Francisco and Oakland, the entire Bay Area is almost entirely automobile focused, just like Los Angeles. And that was a disappointment that there was no, from 1970 to 2000, one could argue that there was effectively no change in development policy in the Bay Area, and it was entirely focused on automobiles. And so this was kind of a disappointment, and people thought that BART would change this, that BART would be a launching pad, a starting point for a change in the way people live their lives and a change in the way people looked at transport, but it didn't do that. And so and this article says that a big factor in that was that you just can't build the transport system and magically assume it will just happen. That the decisions that the towns made on their land development, on their real estate development, on their own, with or without the transport system, are really what affected the growth policies and the transport policies of the Bay Area. So I'm going to take a break. What I would like, if there's anyone out there who has not answered the evaluation for the course, I would like you to do that now, please. So I'm going to take a break and get a refill on my coffee and come back and we'll talk about the evaluation and then talk about the final exam, and that will wrap us up for today. So I'll be right back in about 5 minutes here. All right.